Setting up of boundary conditions as part of problem formulation. This video is part of a course on food physics, of which this series belongs to the modeling section. Now, this particular video is the fifth one in a series of 7 videos, and it's 7 because there's also an intro and there's also a summary one. So even though it says number 4 here, but it's a fifth video in a series of 7, and this one is going to be talking about boundary conditions. It is really intended for a beginner getting into modeling, so we're not getting into lots of details of boundary conditions. Now, as you watch, when suggested, you can stop and apply the principles that we discussed to your own model before moving on to the next step. Now, a couple of things before we get started. The governing equations that we chose, that was the previous video, dictate what type of boundary conditions are needed. Now, boundary conditions come from reality. They are supposed to represent what is going on in the real world, and so that's the second point. But the third one is kind of follows from the second one, because we're using a software typically, or we're solving the equations numerically. It is important that we choose the most realistic boundary conditions, because the software typically can handle a much more realistic boundary condition. This is in contrast to in the lower level classes that we learn of analytical solutions. Analytical solutions require a much more stringent condition to be able to get an analytical solutions, which those boundary conditions may not be a good representation of the reality. Here we can get much closer to the reality, because the numerical solution approach typically used can handle that. So we are about to discuss the most basic types of boundary conditions. Before I get into sharing those, I want to make it clear that this is not intended for the beginner, and it assumes that one has seen these boundary conditions before, like in a heat transfer class or a mass transfer class. If one has not seen these, then there are separate videos in our theory section that introduces these boundary conditions. So with that, I want to quickly go through. For fluid flow, we typically have 0 velocities on surface. That's the most common one on the solid surface, that assumes solid is not moving. If the solid is moving, then the fluid velocity is equal to the solid velocity. For both heat transfer and mass transfer, we have 3 different types of boundary conditions. One is the value given, in this case temperature given, and then the other possibility is heat flux given, like the if you have the food on a grill, so then we know the radiative flux coming in. In case of convection, that's the third type of boundary condition. That's the most common. So you have heating or cooling using a fluid flowing over a surface. So value given, flux given, and convection, these are the most common types. And the same thing for mass transfer. So you could have a concentration given on the surface. Maybe the surface is kept at equilibrium with the surrounding air in drying. You can have flux given. Maybe the surface is impermeable because we have, let's say, an impermeable plastic or foil over the surface. So this flux is 0. So concentration given, flux given, or we have a mass transfer condition where you, let's say in a drying process, so we have dry air flowing over a wet surface, and that uh, condition at the surface that includes diffusion plus flow effect is captured in this mass transfer coefficient, just like the heat transfer coefficient. So these are the most common types of boundary conditions. Again, if you are seeing this for the first time, you should refer to any undergraduate textbook on these topics or our videos in the theory section. Our goal in these slides on boundary conditions is to get more the big picture items. So for example, we need a condition for each variable at the boundary, and we need this condition for all the boundaries of the domain over which we are computing. So here's an example I chose of one of our cake baking model, cupcake baking models. As you can see in the animation on the right, it is modeled using a multi-phase, multi-component porous media transport, meaning there is heat, there's liquid water transport, vapor transport, air transport, air plus carbon dioxide transport, and there is deformation. Okay, so we need conditions for each one. So let's have the schematic. So we're thinking, as you can see, it probably is a reasonable assumption to think of it as axisymmetric. So this is my axis of symmetry here, and then let's look at the boundary conditions that we need for each boundary. On the axis of symmetry, we have all the fluxes equal to 0. On the sides, let's go through one at a time. So let's say for deformation, because the dough is sitting on the metal tray, it does not have any displacement. So no displacement, no normal displacement, but on the top surface, it's free to expand. So those are the three boundary conditions for the mechanics problem, for the deformation problem. Next, for mass transfer, again, because this is a metal surface here and here, so it's impermeable for mass transfer, and here it's also impermeable for mass transfer. But here we have water loss, water coming out, and vapor coming out. So water and vapor coming out. So we include both of them in their respective equations. Then finally, on the surface we have radiative and convective heat transfer. So for heat transfer we have to include both of those modes, and the same on this surface, and on the top surface you have that, plus as the liquid is coming out, it's also evaporating, and so that's taking away some heat. So the main point is that for each variable I need boundary conditions, and I need boundary conditions over every boundary that touches the outside world. So we have 1, 2, 3, 4 boundaries that touches the outside world, and we need conditions on all 4 for each of the variables I am solving for. So again, detailed boundary conditions uh, are discussed elsewhere. So these conditions can get complex. So let's look at an example. This cupcake example is a good one to see that the boundary conditions can get quite complex for a complex model like a multi-phase, multi-component, porous media type of model. So this is just for illustration that the simple boundary conditions that I showed, that you have temperature given, flux given, or convection. Those seem to be the three possibilities. But in this example, I want to show that it's not always that simple. Most of the time it's not, and it can use what is the boundary conditions can set up what is actually going on in reality. So in this heat transfer boundary condition, so flux, let's say on this surface, so I'm just looking at one surface now, I'm not getting into all the details. This is the most complex surface for boundary condition, and I'm looking at only heat transfer. So on that surface I have convective heat transfer, convective, then I have radiative, which can be written different ways as radiative exchange, or in this case it's written in terms of a radiative heat transfer coefficient. So I have a radiative component. So this one says how much radiative heat is coming to the surface. Then as the water comes to the surface and it evaporates, so I have this one. This is the latent heat of evaporation, okay, that's happening at the surface. And then everything leaving the surface, water, vapor, water, vapor, other gases like CO2 plus air. So those are also carrying some sensible heat. So in this case, we ignored the air part. So we have water, vapor, and CO2. So this is sensible heat. Sensible heat. So at the boundary, my condition is the flux equal to convective, radiative, latent heat, and sensible heat. So you can see it can get quite complex, but the point is most computational programs can handle this. So as we are doing the problem formulation, we want to make sure that we are including the most realistic conditions. Now, of course, we have to still use our motto that as simple as possible but no simpler. So if one of these is not really significant, then we don't need to include just because we can. An initial condition is just like the boundary condition, except it is for time. When do we need it? We need it when the process is transient or unsteady. Things are changing with time. Now, in most computational software, we can use for example, initial condition in the domain in the food varying with position. Why would we get a case like that? It actually happens fairly routinely. Here's an example. So, for for example, suppose I have a multi-stage drying process. It's a sequence of drying process. So we first have microwave drying, and then impingement drying, and then hot air drying. This is from the work of Ukidwe. And, so you notice that, let's say I have a model for microwave drying for which we just use some uniform initial moisture content. Okay, but then for the impingement drying, we need to include uh, what is the moisture at the end of microwave drying. Except that in reality, there is sort of a transition region, or the resting region, between here and here. So by then, the material can change temperature, cool down, or dry out a little. And so what we need as the initial condition for the next step, that is here, that can be an unknown. That can be hard to know because of this intermediate resting state. So then one way to get around this is we also model the resting state. Okay, so we model microwave drying, and then we also model this resting or intermediate stage, and that will automatically compute up to this point and then use those as the impingement drying, as the initial condition for impingement drying. And likewise, between impingement and hot air, again I simulate this part so that I know the initial condition for hot air drying. So I just wanted to show you that initial condition, which almost always we assume some constant value, it can have complications and it can be hard to know. Now again, our rule that as simple as possible but no simpler is still valid. So these kinds of complications like we have in these resting zones, at least initially, we can ignore them, and we can use the condition at the end of this microwave drying as the initial condition for impingement drying, and we do the problem, then come back and include these details as a to increase the sophistication of the model. So we should not get into including all of these complications as we are setting up the model first, as is the case now. So now is the time to apply. So I would like you to pause the video and apply the discussions that we had for boundary conditions and initial conditions to the problem that you were thinking of. So you want to think of which variables am I solving and which conditions would be reasonable at each one of the boundaries. Without this, of course, you cannot proceed. Your modeling problem formulation is incomplete very much, because the computer cannot do anything with just the governing equations. It needs the boundary and initial conditions. So try to do this as realistic as possible at the boundary, but at the same time keep in mind that there's no reason to bring in unnecessary complications, or complications that are not likely to be the most important factors in this early stage. That concludes our discussion on boundary conditions. The next video will discuss material properties and other input parameters as sort of the very last thing in problem formulation. If you are interested, or if you missed the earlier videos or earlier topics, there is one on governing equations and one on geometry and domain and goals, and you can go back to these previous videos of this series.